Yeah, awesome. So really quickly, I guess I'll lead by saying I'm not an academic. I actually never went to uni. I think I'm probably the least educated person for about 60 miles from where we're currently standing, which, as much as anything, is meant to contextualize the approach that I took with a lot of this, which very much wasn't kind of like have a hypothesis and test it. It was very like, well, shit, I bet we can get this working. I, having sat in this room all day, really feel like I don't need to evangelize Rust, especially. It feels like everyone is kind of like on board that train, so I'm just going to skip right past this. I will say that like I'm not a hardware person. Dominic, who I forgot to denigrate a little bit for not being here, kind of is more of a hardware person. He's actually a reasonable programmer, but I just take the piss out of him. So anyway, the platform that I was targeting when we were working on this is a great FET. This is one. They're actually pretty tricky to get your hands on, so I recommend like porting something to one, and then Mike will give you one for free. It's basically an LPC 4330 breakout board, which is a sort of powerful microcontroller. It's kind of like big enough to do things on, but definitely a small enough platform that running Linux on it is going to go really, really poorly, to give like some idea of scale. GreatFET is a Great Scott Gadgets thing. Mike Osman kind of open sources everything. He's a wonderful neighbor, as are actual neighbors, which are the like breakout boards for GreatFET. So these are a couple examples of them. My code doesn't actually interact with them. They're just like great examples of things that hopefully will kind of be more supported by this ecosystem soon. So again, like Rust isn't something I really need to explain or sell. So this is like a little bit of a background on what happens when I attempt to do hardware things. I didn't have a JTAG cable, but I did have like a JTAG with a pin header and an Ubertooth with no pin header. This is actually V2. V1 of this hardware had Dominic physically holding both pieces. Because it turns out like if you put a little bit of pressure on them, like the pins contact the edges of the pads. I did like a ton of debugging that way. It was inefficient, so we upgraded. This actually works less well, but Dominic hated me less. So when I first started picking up this project, the idea of like running NOM on the embedded platform was a pipe dream. Like at that point, I was kind of willing to settle for just like getting safe code to run on an embedded platform, and specifically kind of the goal was to have like as little unmanaged code as possible, right? Like if you have like 100% Rust code and very little unsafe, then like you probably haven't screwed anything up. And so there are kind of a few outstanding attempts at doing this in the abstract. Zinc, which is what I'll be talking about a little bit today. TOC, which is this like experimental RTOS, which has kind of everything. So by way of comparison, Zinc basically just gives you a HAL, a hardware abstraction layer, and so it's enough stuff to like let you type code that interacts with hardware. Whereas TOC is an entire operating system complete with the scheduler, right? So in Zinc, you kind of make imperative demands of the hardware, and with TOC, you kind of make logical like requests for things to happen at some point. It's also a really cool blog post by A. Crawford, which basically like builds from scratch hardware support on an M3, which is a chip that is used in a sister peripheral to the GreatFET. So anyway, you need a GreatFET if you intend to do this. Kind of touching a little bit on the last talk, like I, as a non-hardware person while trying to get this going, discovered the Blackmagic probe, which is honestly just the best thing in the world. If you've ever interacted with OpenOCD, you know it's literally the worst. It's kind of this bridge between GDB and your hardware. And so when things don't work, all you can do is like unplug every single junction and like kill all of the software on your laptop and then like bring it all back up in what you believe may be the correct order, and it like might work. Whereas Blackmagic Probe talks the native GDB protocol and just like pretends to be an inferior and kind of does all of that magic for you. And so everything works way, way easier. So getting off the ground, I had to do a bunch of stuff. Like this is broadly what you need to do in order to blink LEDs, which was like our yardstick for success. And so this is basically how we went about tackling it. It turns out that the easiest way to verify our assumptions was to like bring up kind of skeleton code in Rust and then use GDB to just like scribble over memory locations to verify that like the math we'd done for calculating like where memory mapped registers was correct. And one of the really neat things about doing this with Zinc is that Rust kind of provides powerful enough abstractions that you can manifest all kinds of things that normally are either just going to be like binary code embedded in some linker script as like native readable code. So for example, these are the 2 interrupt vectors that you need to supply to bring stuff up on this ARM chip. And rather than being like some magic constants buried in a script somewhere, you can refer to native symbols as option types and provide something that you can usefully statically analyze.
I detect a pattern here. So quite a few pieces of code that are typically ugly at this workshop reveal themselves as beautiful.
Yeah, and so I think like a part of that is definitely like Rust support for procedural macros makes that incredibly easy, right? Like it gives you a fundamentally quite beautiful syntax, I think. Like it's not quite the like ascendant head meme of Lisp, but it does give you a huge amount of flexibility. And kind of because you have the ability to kind of like rearrange things before code gen, like you can sort of like build whatever you want. Kind of on that topic, please stop me and ask questions if I'm moving too quickly or too slowly. This is a little bit stream of consciousness, and so I would prefer to actually like convey meaning than just talk a lot. But so in doing this, we kind of realized that there was an awful lot of like poke memory in our plan. And you know, in theory, the whole beauty of Rust is that you don't do a shit ton of randomly poking memory. And so this kind of brought us down the path of like dealing with the how. So really, really quickly, we successfully implemented a HAL for the grapefat in terms of Zinc. And so now we had like high-level abstractions for hardware features. And you know, once we had this like peek and poke primitive, if you've read any of POC or GTFO, you kind of realize that you can build the world out of it. So I have one demo, but it's not going to be this one. Originally, we had some dancing bananas. Me and Dominic did a dance. It was pretty sweet. But so this is basically what you need, and it's kind of too small to be readable. But this is what you need to like run code on a grapefat that does something useful. And this was kind of the kicking off point for I wonder what we can build out of this. So very, very quickly, like I used a little bit of plumbing because like I've got macros and why not? So I created a function that waits for a while using some inline ASM. I had a macro for turning an LED on, waiting a bit, and turning it back off. I created a bunch of logical pins, and then I went through and like basically just said like turn this one on so it ghost writes across. It was pretty sweet. So this got me as far as I had code running on a microprocessor that was entirely Rust. So there was the typical like I wanted to do something story is like, yeah, I like got Haskell running on like an ARM chip, and also there's like 35,000 lines of C to like make that work. But so that wasn't the case here. It's nothing but Rust code. There are 2 interrupt handlers written in inline assembly, but it still uses a lot of linker scripts. And so apart from the escape hatch that is like the unsafe keyword in Rust, there's also a lot of like, just trust me on this one as far as telling the Rust compiler like, hey, there's a thing mapped here. I promise you're allowed to touch it. Like bad things won't happen if you do. Also, originally we said cargo works natively, and like at that time we fully believed that, but I'm gonna get to that in just one second. It turns out cargo like sort of kind of works natively. The other thing we did at that point was we wanted to know whether or not embedding Rust into a C project works. And like as Jeffrey kind of demonstrated earlier, like in the abstract this is absolutely workable, but we kind of wanted to verify the assumption that you could do this in an embedded context and verify that the underlying principle of like progressively rewriting your scary embedded thing in Rust is like real and achievable. So it was kind of a side note. We ran into a bunch of bugs while we did this, but I think this is by far the funniest one because potentially they could have avoided it by writing object copy in Rust. So we had this like 300-ish K ELF object, and when you literally just tell object copy to copy it as a binary, you get a resulting 258 meg object. And our immediate reaction was like, shit, Rust is like, because we didn't see the intermediate build product, and so we just kind of assumed that the Rust compiler was shitty and had emitted like 258 meg of like turn an LED on and off sometimes, which is like kind of believable. LVM does baffling things sometimes. But so anyway, we went through and looked at the file, and it turns out it was like 300-ish K of like actual data, and then 256 meg of zeros, which we just removed. The funniest part about all this is that we later went back and like actually inspected what we'd done, because like I eyeballed it with XXD and I was like, yeah, like it's all zeros, it's probably fine, I'll just chop them off. It turns out there actually was some data at the end. I don't know, it's gone now, everything still seems to work. Computers, am I right? So yeah, probably not important. So that's kind of where we wrap things up at Troopers. You know, we sort of implied that you could, okay, I straight up said that you could just add things to your cargo manifest and have them work, and that like sort of seemed true, but I guess in retrospect our examples may have been a little too contrived. So this is the part where I actually talk about parsers, like I said I would a while ago. So GNOME has support for building without standard. Standard is Rust standard library. It's on the grand scale of like standard libraries. I guess it's like substantially slimmer than like Go's or Python's that like explicitly attempts to be all things to all people. But it still like has enough stuff in it to be pretty useful on its own, which is actually a problem if you're an embedded platform, because useful stuff normally involves allocating and like interacting with the outside world and doing all kinds of other stuff that like just doesn't work out of the box in an embedded platform. So when I first picked this up, it was just like broken in GNOME because there were no tests and sort of bit rotted. It was a couple of pretty small patches to get it working again. That was kind of the point at which I forked, and so I think things are better upstream now. I actually haven't tried because that's like rule one of embedded development is what I've learned in all this is like at some point you vendor upstream source and then you never ever update it. And then your system will have great security properties. But so this was kind of like the first really big hurdle I ran into with getting this to work on an embedded device. Is like allocation is tricky, it turns out, both because like actually allocating memory in an embedded platform is really, really expensive because all the things that make it cheap on kind of a desktop class processor aren't there. But also you just like don't have that much memory like to start with. And while code size like is a very real constraint, and you know when we thought we'd built a 256 meg object, which is like, yeah, it's not good on desktop, but it's like several thousand times more memory than this chip like has to put code in, it's a real problem. But as kind of like a yardstick, my parser for libpcap, which is like a GNOME parser I wrote like ages ago, just after GNOME was released, because it seemed like a fun thing to do, emits like 100K of code. And for context, like the object it lives within is like 180K. So it's pretty fat, but it's not like devastatingly so. For some reason, I duplicated this slide. But the TLDR is that if you can avoid having an allocator in the first place, your life is going to be way better. A, because you're not going to allocate, and B, it's like a really trivial way to statically detect whether or not your program allocates, because like if it refuses to compile, you're probably allocating somewhere. This is a little bit of like an adjust your needs type thing. Like it's a little like saying just don't write memory corruption bugs, because it turns out like you will absolutely want to allocate, right? If you're, it's all well and good to be like, oh, you should just stream everything through your parser. Like you just never allocate the vector in the first place. You like deal with it as they come in. But that's 9 times out of 10 just like not how the format you're working with works. You can get around it by kind of aggressively kind of statically allocating stuff up front and using them as buffers. But it's definitely enough to get you to like a proof of concept. You can subsequently plug in like a proper allocator later. So the next thing that I ran into is kind of more catastrophic in terms of getting this usefully working. So Zinc is a syntax extension. So syntax extensions manifest themselves as macros in the Rust universe, but under the hood, they're procedural macros. So they are full Rust code instead of just being like a pure transform on your AST. And consequently, they interact with compiler internals, which have no stability guarantees unlike the public API. And so like they're only guaranteed to work with the specific version of the compiler that they were implemented for. This is like quote unquote fine. The ports tend to be fairly straightforward. Like at this point, the compiler is stable enough that it's pretty rare that things get like drastically reshuffled such that you can't get them working again. It's just things get moved around and like identifiers get renamed. However, the version of Rust that Zinc uses also shipped with a broken version of Cargo for like a really subtle feature that you actually need to use to get this working. And so ultimately, like you needed to like both mess with your cargo.toml as well as pass a bunch of like arcane command line flags to get everything to build. The thing that I kind of found funniest about this is the whole appeal of like Rust for embedded is that you stop having to do like classical embedded software things to like write software for your embedded platform. But at this point, I was just like trying random compiler flags, and I like had a make file that would like nuke the universe and like try building it all again on the off chance that would work. Like I was really starting to feel like I was doing this in C. It just like had nicer syntax and a borrow checker to hate me as well. Wow, it keeps the subtitle text. That's handy. So anyway, it turns out that if you're trying to do this like world without collections thing, you can just like take the parts of the universe that you're missing and backport them pretty trivially. The guy who maintains Zinc has this really sweet crate called Rust libcore. And what it does is with a build script, it works out what version of the compiler you're using, and then it like reaches out to GitHub and fetches the tarball of the source for that. And then it takes libcore out of it and it like uses sed to adjust some imports. And then it builds you a libcore. And now you have libcore, because you're not meant to use the one straight out of the compiler. But it's, you know, I mean, in spite of being like a huge egregious hack, it's also like, I don't know, you're building this for GreatFet, what do you expect? And that is still like materially less shitty than all the other ways. Like the alternative is re-implementing libcore yourself, which is probably going to be bad. There is now support for not having allocating collections at all in Rust, I think. I'm looking at Jeffrey to see how much he nods. All right, there's kind of support for it. But for me, that was problematic partially because it didn't seem super useful, and also because I didn't want to write any new parsers that didn't allocate, and my test case that I already had that I was planning on using allocated a lot. So I just went down by hand and did exactly the same thing that he'd done for libcore, but I did it for liballoc. So I took liballoc out of the compiler. I like futzed around with some import paths. It does some like bizarre cargo trickery to work out where everything is. So I just kind of did that, and then I linked it into nom, and then like, great, I now have an allocator. There's some substantial performance overhead, but like it's fine. So, like I think in terms of things to materially improve on, like this is the bigger one, right? Like if nom has kind of a first class notion of allocation instead of just like using native data structures, suddenly this doesn't become a case of like ripping out chunks of the compiler. Instead, you just need to implement an interface that allocates, and like you're off to the races. And so I think this is like the next big thing to work on. So the next thing that went wrong is compilers are terrible. So Rust C uses a lot of LLVM, as you probably know. And so LLVM's linker is like the last thing to kind of make LLVM, or Clang, I guess at that point, be like a big boy compiler that you can build everything out of. Their linker is like fine, but it's subtly broken in enough places that even projects that have migrated to Clang and LLVM still tend to use GNU's linker. And so this is a classic example of that. It turns out Rust has CC hard-coded in exactly one place. And so in spite of the fact that I told Rust C via Cargo that I was building for Thumb v7, it just like shells out to, oh shit, I'm running out of time. I have to go really fast. In spite of the fact that I told it to use Thumb, it like shells out to the system linker, which then, in spite of the fact that the actual problem is that I'm trying to link a bunch of ARM objects together with an x86 linker, what it actually says is relocation and generic elf, which obviously tells you what's wrong. Compilers, right? So I fixed this by creating a shims directory and adding it to the start of my path where I just symlinked that in. The funniest part about this is that it turns out it also tries to generate native code elsewhere in the build process. And so you just like alternate building it with the two linkers, and it kind of like ratchets its way through the build process, and like eventually you get an elf object. In terms of like, would I do this in production? Maybe. I do have a demo that I want to quickly show just because I think it's neat. I'm also going to blame Dominic for it not being ideal. Oh god. Now, I think if I tmuxed hard enough, yeah, this is totally going to work. Okay, so This is like exactly the same as my Knight Rider demo before. The one difference, so the reason I'm doing it this way is because IO is currently kind of broken on GreatFet, or at least the IO that I needed to use for this. And so instead of using native IO, I'm kind of using my Knight Rider demo as an oracle. So what happens is it creates some bytes, it parses them with nom, and then assuming that all of these assertions hold, it will then like do its blinky little Knight Rider demo, and we will have parsed some stuff on nom. It'll be great. This is the like janky harness, like this is the horrible command that you have to run to build everything. And then hopefully my shell history up here somewhere is the GDB script to load it onto a GreatFet. I did this like literally an hour ago, and then I dicked around with my demo for the rest of that hour. It was great. Wait, neat. Okay, so this loads it onto the GreatFet, and now it's like doing the Knight Rider thing. Awesome. But so like the practical implications of this are kind of a fewfold. Like probably the biggest one is that like the parsing aspect natively works, right? Like that was the conclusion we arrived at Troopers when we like ran cargo build in the build directory, and we're like, hey, like great, like nom builds, awesome, we can probably do this. It turns out that all of the actual challenges are in like bolting it to other things. And this kind of brings me to like all the things that are horrible about this. Zinc is really challenging to work with. There's a sweet bug where if you rename the directory that this project is in, it just stops building with an error message about libc. Like it doesn't cognitively make any sense to me or anyone else that I've spoken to, which is why the project is now called blink_LPC 1700 forever, because that's the only directory it builds in. The compiler errors are all terrible because Zinc is made of compiler plugins. And also like it still turns out that it's hardware. When we got this working originally, we wasted the best part of a day because Dominic drew me a diagram, this diagram in fact, and like I thought that the numbers were going sideways instead of horizontally, and as a consequence I put all of the wrong offsets into a linker script, which was terrible. So this was where my demo was going to be. I wanted to get it done in case I ran out of time. But yeah, so like in terms of conclusions, like this is like, it's great when it works, but Cargo is still like really, really immature because no one's testing any of these code paths for like cross-compilation to unsupported architectures where you're not using the standard libc and you're passing in a second allocator and you're using weird features to control compilation. Like you're completely off the reservation if you try anything like this. And so you like will spend days and days and days doing the like classic embedded development thing where you just like randomly try things out of your shell history until it works, and then the next morning it doesn't work anymore, or you start checking all of your artifacts into Git just so you can like go back, for example, to do a live demo. I totally had working ones in my Git history just in case. But yeah, the flip side, I think the biggest thing I learned from this is that the resource constraint remark that I made in my abstract was actually a lie. Like the problem right now isn't necessarily resource constraints. Like compilers are good enough, and if it really comes down to it, you can totally unwrap your parser to kind of prevent yourself from storing so much state in PC. Like infrastructure constraints are now like the big problem facing us. So hopefully I have like 45 seconds left for questions. Yep.
I have a question that's kind of off the direct path at which you were going.
Great.
So you were talking about, you essentially wrote the how, right?
Mm-hmm.
And you basically came up with primitives that you wanted and you translated into what the GreatFet could do, right?
Yeah.
So when I wrote the software layer for the good Fed, I ended up doing the exact same thing.
Yep.
So do you know, and which is essentially a VM, right, on which we build everything else?
Yep.
Do you know of sort of more general, does anybody know more general VMs for microcontrollers like this that we could just all build on top of?
So I think arguably Zinc tries to be that. I guess as a concrete example, like Zinc exposes a pin trait, and so you just like implement pin, and you know you have to supply the like necessary plumbing to make like on and off do the thing like cause a pin to go high or low on the hardware. And so I was talking to Jeffrey about this a little bit before. Like, I think that's broadly kind of cool in this like hypothetical dystopian future where you buy a temperature sensor and it like comes with Rust code on a USB stick, right? Because then like, as long as your hardware that you intend to like plug the temperature sensor into the GPIO pins like implements the pin trait, you kind of get all the wiring between like the physical temperature and like a floating point value in your code for free. I think that largely, I mean, it doesn't mechanically satisfy the definition of a VM, but in terms of kind of giving you that substantial abstraction, I think it totally does. The other way to tackle that is to go down the RTOS path, right, where you just have a syscall boundary, which is like typically how it gets solved. I think mechanically that like HAL approach of just using the trait system to your advantage is probably the right way to go. And I believe that almost entirely because of overhead. I mean, it turns out if you need a scheduler, like you're probably better off using someone else's, but especially for kind of the really resource constrained environments that we're hoping to target, like I would like to be able to get kind of the glue code down under the like 15, 20K mark. Like at that point, the chances that you need a scheduler are really slim. You almost certainly like polling some stuff and doing things when things change. Does that answer your question?
I think so.
Cool.
Some engineering challenges. Nevertheless, proof of concept is right there.
Awesome. Thanks so much.